listeners. I welcome you all to another episode of my weekly and online chemistry class. This is episode 3 and episode 4 of season 8. In the previous episode, we talked about the first factor that affects the polarity and as well determines the reactivity of organic compound, that is the inductive effect. And I told you it is of two types, which can either be negative or positive. We are going to continue from where we stopped, as we'll be looking at another factor entirely today, which is hyperconjugation. Hyperconjugation, or the so-called hyperconjugative effect. The hyperconjugative effect is a permanent effect that occurs when there is localization of sigma bond of alpha hydrogen of an alkyl group attached to a pi system or to an empty p orbital in a particular compound. What we mean by this can be in two forms from the definition. For instance, if you look at an ethyl group, ethyl carbonium ion, the carbon atom carrying the positive charge has an empty p orbital. But this carbon atom, which is an alpha carbon, I think I need to quickly take you through that. When you have something like this, CH2, 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 COH, this is the functional group in this molecule. The carbon that is next to it is called an alpha carbon, and all the hydrogen atoms on that carbon are called alpha hydrogen. The one that is next to it is a beta carbon. So this beta carbon also has two beta hydrogen, as just like these two alpha hydrogen on this carbon. The carbon that is next to it is a gamma carbon with two gamma hydrogen, while the one that is next to it is a delta carbon with three delta hydrogen. So here, this is the carbon that is carrying the positive charge, the carbonium ion. The carbon that is next to it is an alpha hydrogen, and that carbon atom has three other hydrogen atoms. So there are three alpha hydrogen on this carbon atom. Don't forget that the hybridization of this carbon atom is sp3, bonding with an s orbital of this hydrogen. So because the s orbital of this hydrogen, this sigma bond, which is formed by overlapping of s orbital of hydrogen and sp3 hybrid orbital of carbon, has some kind of overlap with the empty p orbital of the carbonium ion. So that relationship is what we call hyperconjugative effect or hyperconjugation. So that means in a thick carbonium ion, there are three alpha hydrogen and you can form three hyperconjugative structure. I don't want you to misquote or misunderstood hyperconjugation to resonance. Resonance, we are going to discuss that later, is the delocalization of pi bond electrons between two or more atoms or lone pair of electrons in a pi system, and that usually results in the formation of what we call resonance structure. But in hyperconjugation, it is sigma bond that is involved in that particular effect and not pi electrons or lone pair of electrons as we have in resonance. So here, the other type of this effect is what you have in a pi system. Take for instance, you have something of this nature. Then there are three alpha hydrogen attached to this carbon of the carbene, the carbon atom with double bond. So this is an alpha carbon to this carbon. So in that case, this carbon also has three alpha hydrogen. So there can be a kind of hyperconjugation whereby the sigma bond electron between this S, the sigma bond of the S and sp3 hybrid orbital of this carbon can come here to form a double bond, while in that case, this pi bond here can move away from this carbon atom towards this carbon atom to give you a hyperconjugative structure of C, H, H, then H, and you have a double bond here, then you have hydrogen here, you have a carbanium, so this must have a positive charge, and you have something like this. Now, there can be three of this kind of structure from here, because when this hydrogen is involved, this hydrogen will be like this in this form. If it is this hydrogen that is involved in the hyperconjugation, then you are going to have another structure. Meaning, from propane, there are 3 hyperconjugative structures that you have. Then, if you look at this structure, this hydrogen ion that is positively charged looks as if it is free and not bonded to this carbon atom. But that is not true. Although it is not bonded to it, but it is not free to move about. It is still attached to the carbon atom in one way or the other. And that is why hyperconjugative system is also known as no bonding resonance system, because a bond does not exist between this hydrogen ion and this carbon atom. And I told you that you are going to have at least 3 types of hyperconjugative structures from this structure of propylene. So that means a hyperconjugative structure or hyperconjugation, it has a lot of advantages, and there are some things that can be obtained from hyperconjugation. One, it results to shortening of bonds. Shortening of bonds. If you look at propane, for instance, the bond length of carbon-carbon single bond is longer than that of carbon-carbon double bond. I've taught you hybridization in one of the, I think it is in episode 2 and 3. You may go and watch those episodes again to understand what I mean by hybridization. The hybridization of this carbon atom is sp3. The hybridization of this carbon is sp2. Where, as a result of hyperconjugation, the hybridization of this carbon is sp2, while this is sp2. You can see that because of higher degree of S character, this carbon-carbon single bond is longer than the carbon-carbon double bond here. This is one of the effects of hyperconjugation, because it usually result to shortening of bond. Although you may say this bond becomes longer as it is shorter here, but this becomes shorter as it is longer here. That is one of the effects of hyperconjugation, shortening of covalent bond. The other effect is it can be used to account for stability, for the stability of alkenes. I want you to compare this. CH3, then C double bond, CH2, and CH3, C, hydrogen double bond, C, hydrogen, CH3. This is propane, this is butane. In propane, there are just 3 alpha hydrogen, meaning you are expecting 3 hyperconjugative structures in propane. In butane, there are 6 alpha hydrogens, 3 from each side of the double bonds. There are 3 alpha hydrogen here, there are 3 alpha hydrogen here, making a total of 6 alpha hydrogen. So that means you are going to obtain a total of 6 hyperconjugative effects. And as a result of that, butane is more stable than propane. And that can be determined from the enthalpy of hydrogenation of the double bonds. Another example, so when you have an alkane of this type, double bond, CH3, 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 with 12 alpha hydrogen, this is more stable than when you have double bond, CH3, hydrogen, CH3, CH3. This is again more stable than when you have C double bond C, CH3, hydrogen, CH3, hydrogen. And that is more stable than when you have an alkane of this type, CH3, CH, double bond, CH2. So the higher the number of alpha hydrogen or alpha carbon with alpha hydrogen attached to the double bond, the more stable the alkane. So alpha conjugation from this demonstration can be used to explain the stability of alkane. Another important effect of hyperconjugation is stability of carbonium ion. In our subsequent episode, we are going to discuss the different types of carbon that we have and their stability. Carbocation. So we observe that tertiary carbocation with more alpha hydrogen. Look at this. CH3, carbonium ion. This is more stable than secondary carbonium ion with 6 alpha hydrogen, CH3 plus. This is more stable than primary carbonium ion with 2 alpha hydrogen, and that is more stable than methyl carbonium ion with no alpha hydrogen. So here you can have 9 alpha conjugative effect, 6 alpha conjugative effect due to the presence of 6 alpha hydrogen, 3 alpha conjugative effect. So this is a tertiary carbonium ion. An example. This is a secondary carbonium ion, this is a primary carbonium ion, while this is a methyl carbonium ion, which is also an example of a tertiary carbonium ion. Another effect of hyperconjugation is observed in alkyl benzene, and that is one of the factors that relate that the methyl group attached to the benzene ring is an auto-para director. Let me draw it in a proper way. When you have something of this nature, methyl carbonium ion, there are 3 alpha hydrogen here. As a result of hyperconjugation, you are going to have something of this nature. Carbon, hydrogen, hydrogen, then hydrogen ion. This is negative, you have another stability here. So in that case, you can have another hyperconjugative structure whereby there is a double bond here, hydrogen, hydrogen, then you have this, and there is a double bond here, negative charge. You can have another hyperconjugative system, and that is what we have like this. Oh, okay, double bond, negative charge, carbon, hydrogen, hydrogen, then you have the hyperconjugate. So here there are 3 hyperconjugative structures of methylbenzene, and from the 3 hyperconjugative structures, you can see that there are negatively charged carbon at the auto positions here and here, as well as the para position, indicating that the methyl group attached to the benzene ring is an auto para director and not a meta director. So hyperconjugative system conjugation can be used to explain that. So you can observe that hyperconjugation also involves sigma bond, like the inductive effect, which takes place in saturated organic compound. But have it in mind that the hydrogen ion is still bonded, although not bonded with the carbon atom, but it is not free to move about. With this, I believe you have learned 1 or 2 things today as regards hyperconjugation. So in our next episode, we are going to look at another factor, and the application of this factor will be considered later when we get to physical properties of organic compounds, as well as various types of reactions that organic compounds do undergo. Thanks for watching. Do have a wonderful day.